going to do geometry. I'm going to try to hit all the topics we're supposed to. There's quite a bit really to hit in that time, but I think I've done it to where we can do that and hopefully get out a little bit sooner too. So, because I know it's Friday and I really recognize some of y'all's dedication, okay? So, I appreciate you coming. I'm hoping by 4:15. I would love by 4 because as much as you're tired in my face, I'm actually tired in y'all's face too.
Understandable.
Okay. I really feel like I have actually taught like 2 weeks now instead of one. Okay, so basics. I'm going to start with circles, then we'll go to triangles. Can we stop talking? So I want to start with circles, then we'll go to triangles from there. Basics of circles, I think most of you are okay with. You know, obviously a circle has equidistant sides from the center. I think everybody's okay with diameter and radius. I haven't seen any issues with that concept. So diameter is the full length across to the center. Radius is half the length. And we know a chord is side to side, but it does not actually go through the center. So a chord can be anywhere on there except for it cannot touch your center. Okay? It must touch one side to the other. So it can be a really short chord. I could even have one that went from here to here. Or it could have been longer and it could have went almost to the middle. So you have many options for chords. Okay. Anybody have questions about the definitions of the main stuff? Okay. So we should know by now if I ask for the area of a circle, and this is, you know, going back some, it's pi r squared, and that the circumference is 2 pi r. Now that's important to remember because you're going to have to be asked, as you've seen through the released items, at some point to either calculate the arc length or the area of the sector. And both of those formulas are needed for those. I'll get to those examples in a little bit though. Circles can help you solve for a couple different things. The first is lengths of segments. Whether it be inside or outside. We're going to cover that. You can solve for lengths of arcs. You can solve for degrees of arcs and degrees of actual angles inside of it and outside. And remember, if it's not in degrees, it could also be in radians, which we've talked about. So we're going to look at inscribed and central angles. Sorry, I didn't mean to write in cursive. It just kind of happens sometimes. Okay, if you struggle to remember which one's which, central is literally from the center out. So if I have a circle, remember this whole time we don't judge on my drawing abilities. Okay, a central angle will have from the center at my vertex and then it'll connect to the other sides. If I wanted this and I told you that this outside arc, I'm going to kind of squiggle it so you can see what I'm talking about. If I told you it was, we'll say, 290 degrees, can you tell me how I'd find x? Okay, not. You said find the other arc, right? Is that, I can't hear. You gotta remember. Okay, so how do we find this other arc? 360 minus 290, which is 70, right? Now, so that part you was okay on, but a central angle, it just projects whatever it is. I told you the example of the flashlight. If I might put a flashlight in the middle of the room, it's normal, it's projecting, but as I move back, it gets bigger. My beam stays the same. My beam can't change, but it gets bigger. Well, it kind of works reverse with a circle. If I have a circle, okay, I guess you could see it either way. But instead of this getting bigger, my 70 may have stayed the same, but the beam is getting smaller. So, and remember, this is not drawn to scale, okay, at all. Like, I have no idea what these are actually. But this becomes half, which is 35. So for a central angle, it doesn't have that chance to go back the other halfway to make it half. So it's actually only 70 degrees. Okay. So inscribed is what this is. It halves, or if you're reversing, it doubles. And then central angles are actually what it's projected as. Is there any questions about that? I'm going to show you one of the more complicated problems for inscribed. Okay. So I made up a bunch of examples. I'm going to zoom in. Just give me a second. Okay, so this is a bunch of inscribed angles that'll help you find it. As you can see, this is the angle that you want. Okay, this is the arc that it intercepts. So if I can just find what this whole arc is, which I already know 106 of it, then I'll be able to find what this is by dividing by 2. Okay, I'm going to have to do that in a couple different ways. I'm going to have to kind of play with it. If I know that this is 113, I know what this side is, right? Because I'm going to switch colors. This projects onto this arc. Well, if this is 113, what is this green arc?
226.
Okay, how did you find it? Yeah, you're just doubling. So we know that this whole thing is 226. We know 106 of it, right? So just go 226 minus 106, and what do you have? You can say it, Chase. 120. So this side's 120. This is 106. This is 64. Now I could find this little piece to be able to complete this section right here that I needed to actually find my true angle by dividing by 2. So now I'm just going to go 360. Well, I'm going to add up 226 plus, blessed Jesus, 106 plus 120 plus 64, and then say 360 minus that, which is 70. So this is 70. Then I just go 106 plus 70 is 176. And then divide that by 2. And you get 88. Anytime that you see something pulled back in it and touching, the vertex is touching the thing, think of inscribed angles. Now you may have to play with some other things, project it somewhere else, stuff like that, but you can still use inscribed angles. Is there any questions about that? Does anybody not understand inscribed angles in any way? Okay. So I'm going to leave that one alone for now. And central angles we got, so let me mark that off. Okay. So that's the really extreme basics. I'm going to also talk about how to find arc length and arc sectors, area sectors is what I'm trying to say. We talked about arc length quite a bit today. We've done 2 problems with them today in class, but it's not going to hurt you to see them again. I zoomed super in, so I'm going to zoom back out. So we're going to start with arc length. Now remember, there's 2 ways to measure an arc length, which is like if I needed to have a piece of string to draw that circle out, I would need to know how long that string is. And then we have arc measure, which is actually the degree measure that's projected in some way by central angles. So arc length is, I'm going to take it. To do arc length, you have to have 2 things. You have to have the radius, and you have to have the degree of whatever that angle is. Okay, this means that we are trying to find the length of this. Okay. So we're going to stick with our 70 just because we have it right now. So 70 degrees. And I'm going to say that my radius is 3. It could tell you the diameter. We've also seen the problem where it worked backwards. It actually told you the arc length and it wanted you to find the degrees. It could also want you to solve for the radius. Be prepared for any of those, but you have to know how to set up that formula. I told you in class I didn't expect you to know the formula off the top of your head, but to think through it. If we're talking about length, are we going to deal with area or circumference? Circumference, very good. So 2 pi r. That's a formula that by now that is probably embedded into your brain. You've heard it 1,000 times, not just in my class, but in others. Okay, so we have 2 pi r for the circumference, but this is for the whole circumference. That would cover our entire circle. We only need 70 degrees out of it. So we literally need 70 degrees out of that total 360. So I'm going to multiply it by that. You take your degrees, divide it by your whole, which is 360, and multiply it by your circumference. Okay, so we have 70 over 360 times 2 pi times 3, because r is your 3. Does anyone have questions how I got the formula or how I plugged anything in? Okay. After that, you just type it in. Always look for the answer choices because, I mean, we're preparing for a test at this point. So if it has pi in it, then don't type pi into your calculator because it's just going to be in pi terms. So it could have done this. 70 divided by 360. I picked the bruised one, sorry. And then times by 2 and times by 3. Notice I didn't type in pi at any point, right? And obviously I made up these numbers, so it's very possible it's not even come out to a perfect fraction. Oh, but it did. Looky there, how pretty. And so it come out to 7/6, and then you put pi beside it. Now, if instead it gave you a decimal answer, go ahead and type in pi. No big deal. You're just going to say what we had before, but times pi. And then your decimal would be 3.67. So always go with whichever way they give you. They may have even given you 1.17 pi. Okay? But you know how to look at answer choices and play with that. You've had to take these stupid standardized tests long enough to know that now. Unfortunately. Is there any questions about that? Okay. Same concept of area of a sector. We're not going to find the area of the whole circle. We just want to know area of a portion of it. So you would take whatever the degree is. We'll say 70 also. And 3. We'll use the same example. But this time, I don't want the length of the arc. I want the area of the sector. Which means I want whatever the area of this little piece is. My phone's freaking out. So. Oh, it'll be fine. I don't even know where it's at. Okay, we're good. So, now what formula am I going to use as my starting formula? Yeah, so it's pi r squared for area. So we go pi r squared. And then you're still using that concept of what proportion of that circle is it? Well, it's 70 degrees out of the 360 degrees. So 70 out of 360 times pi times 3 squared. And you'd still type it into your calculator from there. I mean, that part's not any different. The only difference between area of a sector and the arc length is which formula you use, either pi r squared or 2 pi r. Now, if this had not said degrees, if this had given me pi over 2 radians, okay, what do I do instead? What do I change on my formula? What's radians another thing for? No, but go with the concept of what it connects to. It's radians versus what? Degrees, right? So where's my degrees in this problem? The 360, okay? And also the 70, but obviously it wouldn't have given you the 70. It would have gave you like pi or something. It would have done something like that. So that's what you change out of the formula. Instead of 360, it is 2 pi. Remember, 1 pi is 180, but 2 pi is 360. So it'd be x over 2 pi times either area or circumference, whichever one you needed. So if you originally, even if it's in radians, need to go ahead and write down that 360, just so, because that makes sense to your brain because you dealt with 360 all your life, that's fine. Just go back and change it at the very end before you actually type it in. Is there any questions about that? Okay. Also make sure that like when you're dealing with sine, cosine, and tangent or anything like that, your calculator's in the correct mode. So when you're talking about radians and degrees, do that. If you cannot remember to switch it into this and you got a degree answer for however you did it, even though it didn't give you a pause, but it said, hey, I want the answer in radians, make sure you do the conversion. So if I told you it was 90 degrees, that you need to get rid of the degrees. So over 180, so pi over 180. So for those of you in chemistry, I said that's not too bad of a concept because you're used to canceling out different units, right? Well, you're canceling out the degrees. That's why one's on top and one's on bottom. And then pi represents the radians. So your degrees would go away and become pi. 90 over 180 is 1/2, so 1 pi over 2 is what it becomes. I don't expect you to have to do that, but if you need that out, you always have it. If you couldn't remember that 180 is pi, but you remember 360 is 2 pi, you could have also used that conversion, just 2 pi over 360. Either way, I don't care. Okay. Okay, so that covers arc length and our area of sector. Does anyone have a question on either one of those?
Okay, wait, what's the pi with the 3 squared?
This was, we were solving for area of a sector, right? Are you okay with the 3 being radius?
I am now at note 4.
Okay, yeah, r means radius, and I said my radius is 3, so I did 3 squared.
Okay, cool.
Is that okay? So are you okay with everything else on it?
Yeah.
Okay. And then just type it in. I didn't type it in for y'all, but. Okay. Any questions on that? Okay, so now we're gonna talk more about angles that form in different ways, whether it be tangent lines, secant lines, stuff like that. The good news is the rules for the outside angles is really, it doesn't change at all. And it's very similar to that rule of an inscribed angle. And I'll tell you how they connect in just a minute. So if I have this, and I want to know what this angle is, I have to know or be able to find out in some way whatever this arc is, the big arc that's intercepted, and whatever the little arc is. Okay, so if I said this is 200 degrees and that this is 80 degrees, I need to be able to find this, right? Well, on an inscribed angle, one that didn't go all the way out but stopped right here, we would have just divided that 200 by 2. Okay, but I need to equalize it back to where, what would it have been if I had had it here? So I have to say 200 minus 80, then divide it by 2. So 200 minus 80 is 120, divided by 2 is 60 degrees. Okay, that kind of makes up for the situation of it not, if it pulling all the way out instead of staying inside. Where if you think of an inscribed angle, it did the same thing. If that was 200, which is not, because I definitely didn't draw that correctly. What would this be? Well, we know it would be 100, but it's 200 minus, oh, I didn't intercept an arc, it had 0, right? Divided by 2. So it works the same way in the same concept if you can just remember the big minus the small divided by 2. They will not always tell you every little piece of information, so they may not tell you the 80, but they would have to give you some kind of clue. So they could make that a center point, and then from there they make you find different information. They could give you maybe these two, and you'd have to find that by knowing this part's 180. Okay? Or they really like to do this, if I can draw it accurately. They use 2 tangent lines and just tell you one of them. So they could tell you that this is 300 degrees. If that's 300 degrees, what do we know about this? It has to be 60 because that would make up our whole circle. So then they would expect you to go 300 minus 60, then divided by 2. Okay, so just be prepared that they may not tell you straight up what each little arc is. You may have to manipulate it in some way to find it. Is there questions about that? I'll see if I find a good example. I don't know if I have any. Okay, what kind of lines did I say these are? Tangent. Remember, tangent lines just touch it and keep moving on. They never actually go inside of it. I gave you the example of like going off on a tangent. So like I'm telling you a story about my dog chasing a squirrel, and then you sit there and you're thinking about squirrels eat nuts and your favorite nuts is pistachios. And so you decide to tell me that. Your brain just went off on a tangent. It connected to the subject just a tiny bit, okay? But then it went in a totally different direction. So that's how I keep them straight. A secant literally goes through it. So both of these would be considered secant lines. These are 2 secants, these are 2 tangents. You could have combinations or just all of one. It doesn't matter either way. We also have ways to find not just the angle, but how to find the segment link. So this is something that I went over with y'all like 1,000 times, but you know, you've slept since then, so I don't expect everybody to remember. Okay, let me find examples, because every time I make up problems on these, it gets a little interesting sometimes. Which is fun. I don't find it interesting. Y'all seem to find it. Okay, so I'm going to do 2 secant lines first. And keep in mind, this is probably not drawn to scale. Don't judge. If I said this was 8 and this is 7, and this is 13, and this is 2x plus 5. Secant lines are much harder to deal with because you tend to make a very small mistake, but it's a very small mistake that makes a big difference. So secant lines, anytime you have a secant line, whether it's in conjunction with another secant line or with a tangent line, it has the same rule every time. It is always the outside part times the whole line. Okay, so if you have 2 secants, if you have a secant equal a secant, then you're going to have an outside times a whole equals the outside times the whole in the other line. Okay, so the outside on this, I want to look at this line, is 8. The whole line is 8 plus 13. The biggest mistake I see is you want to go 8 times 13 because it just seems natural to you. Please don't do that. It's a mistake that even I make sometimes as I'm going through it. It's just really easy to write down, but it's outside times the whole line. So outside times 21 in this case. And then 7 times, this is 2x plus 5 plus 7, right? From a whole line. So this whole line is actually 2x plus 12. Does anybody have a question or not understand how I got that?
How did you get the 21?
I said 8 plus 13. Any questions?
How did you get 7, 2x plus 12 and multiply 8?
Okay, so what I'm doing is this first line equals this second line.
Oh, okay. I thought you meant equal.
No.
Other than the second line.
Yeah, no, they're both secant lines, so they both have that same layout. Does that make sense?
It does.
Okay. Any other questions? Okay, so from there you saw, so 8 times 21, 168, I think. I don't know, it's kind of Friday, so I probably need to check that one. Telling you, right now it's a struggle. Yeah, okay, we're good. And distribute your 7, so 14x plus, I think, 84. And again, yeah, okay, good. What do you got me? From there, you subtract, you go 168 minus 84 is 84. And then divided by 14, which is 6. Okay,
Myra Morgan, please call 602. Miss Morgan.
okay, so they could ask a question about this in a couple different ways. They could simply say solve for x. They could also say, what's the length of segment if this was like ABC? They could say, tell me the length of segment BC. They could ask for just the segment of, make this like a DC. So they could do it in a couple different ways. The one that I picked, because I told you I just got it off the paper, it says what's the segment length of BC. Okay, so you would have to take the 7 plus 2 times 6 plus 5 in that case. So 7 plus 12 plus 5. And you get 24. So just be able to read and understand what it wants you to find. Because it's really crappy if you can actually find x and do all that work, but then you don't understand what it's actually wanting. And it's very possible that they would have given x as or 6 as an option in your multiple choice, just to see if you can read and comprehend what they're asking. Sometimes they do that, sometimes they don't. Is there any questions about that? I'm now going to do a secant tangent, and then I'm going to leave it at that for those. Okay, a secant tangent, I think tangents are easier. I don't know if that's just because I want them to be easier, so they are. And I don't think I see an example, so you're going to have to live with whatever craziness my brain comes up with, which will be interesting, but that's fine. So don't be surprised if you get a decimal here. Let's do x plus 3. This is 5, and this is 7. It's very possible we can come to a negative, and that's fine. I go with it. Okay, secant is still the same rule. It is still the outside times the whole. But when we set it equal to our tangent, tangent's always squared. So whatever it is, squared. Okay, so you can put an X, it's just a squiggle. Just a squiggle. I hesitate to put X because you have an X right there. I don't want you confused. Okay, so outside times whole, we're going to do it again. 5 times 5 plus X plus 3, which is X plus 8, equals 7 squared. Is there any questions about that? Okay, distribute 5x plus 40 equals 49. It's going to be a decimal, but it's not going to be negative. That's the plus side. Okay, subtract 40, and you get 9, and divide by 5. So 9/5 or 1.8. Either way. And then yet again, if they asked you for that whole length, you would have to add them, something like that. Okay, so tangent's always squared. Secant is always the outside times the whole line. So if it's a tangent and a tangent, they're always going to be the same. So if I had a circle here, okay, because it's something squared equals something squared, it's always the same thing. So even if I had like 7 here and x plus 3 here, it would be 7 squared equals x plus 3 squared. Well, if they're both squared and there's nothing else like on the outside of it making them different, then it's just 7 equals x plus 3 in that case. So x would equal 4. So just kind of keep that in mind. That's kind of the proof behind why tangent and tangents are always the same if they meet at the vertex on the outside. And we're going to see an example where that's helpful to know in just a second. Does anybody need more time to see that before I? Okay, that's fine. Does anybody have questions so far? You good now? Okay. So here's a weird example. I haven't done one of these in a while, so let's just see how this goes. I'm gonna zoom in. I'll give you a minute to write it down. This is a circle inscribed into a quadrilateral. And it's made up of a bunch of tiny little tangent lines.
Why did you just say square?
Because it's not a square.
Is it not?
It's not even.
Look how, yeah.
Well,
Maybe I just wanted a fancy word.
what they were saying. You impressed me that.
I'm so glad. It was my dream come true.
And I know that's what y'all, you try to do.
Exactly.
Are we supposed to draw this?
Some people want to, some, if you don't want to, that's fine. I'm not going to attack either way. I just wanted to give time for those who did. Okay. So this is one of the things you're going to piece it by little piece. I like these because it's like a little puzzle. Like you find one piece and you fit it to another. Because of tangent lines and how they work. So like right here, if this is 3.3 right here, this little piece right here is also 3.3. Okay, and the goal is just to find the parameter. So I have to find everything on the outside. I probably should have showed you that, but okay. If this is 3.3 and this whole thing is 12.3, then how could I find this piece? Yeah, you just subtract. It's really not that big of a deal. 12.3 minus 3.3 is 9. So this little portion is 9. And if that little portion is 9, then this little portion is 9. So maybe you kind of see how I mean by it's a puzzle piece. Like one little piece takes you to the next and takes you to the next. Because you now know you have 15.2 minus 9 to get this other portion. Right? So that's 6.2. Does anybody have a question about that so far? Okay. And now if I know this is 6.2, this one's 6.2. Okay, this is just what tangent lines tell me. So this is kind of where they could test you on tangent lines. And if that's 6.2, 15.1 minus 6.2 is 8.9, which makes this 8.9. I find that because I know parameter means that I'm just going to add up all the numbers on the outside. Now, here's a mistake with these kind of problems. People tend to like add up all the numbers, but 9 and 3.3 make up the 12.3, so don't double count it. So what I always do is I erase my big numbers before I accidentally add them in as I'm just kind of typing. So you just add in every single one of these numbers and you'll get your parameter. Is there any questions about that? Okay, so I'm not saying they're going to have an exact question like that, but it's very possible they'll do something in which you have to show that you understand tangent lines are congruent when they meet at that point and they come down. list. Okay, got that. We're almost done with circles. We got intersecting chord theorems, and then we're going to quickly look at a graph of it. So intersecting chord theorems, I'm going to have to use, we're going to use this example. Okay, so this one says find L of n, which means I have to find this whole thing. But I have to be able to find the actual different portions. Now, the formula for this one is you take an entire line, so like L of n, and you say 3 of x times 2x plus 2 equals 15 times 8. So it's that portion times that equals this portion times this. Okay, you may kind of remember that. That may ring some bells. I don't know. Oh, you can't see it. Sorry. I don't know. I don't notice these things. This one will be a little bit harder because of the 3x and the 2x, it's going to distribute it and it's going to create a quadratic. Anytime it does that and you need to find out which it works, you can always graph it and find where it crosses the x-axis instead of having to factor or whatever. But that's up to you. So it would give you 6x squared plus 6x equals whatever 15 times 8 is. I'm sure I should know that too. 120. You could factor this. You could pull over 120. I would take a 6 out because, well, that's some big freaking numbers. Does you have questions so far? I know I do that kind of fast. But if you're not comfortable with the actual factoring, that's fine. If you put that 6x squared plus 6x minus 120 into your calculator, you can see where it crosses the x-axis. After I solve it with factoring, I'll show you that way. Okay? Yes.
How do you know like how you're supposed to set it up? Like, in what order?
If you see that lines are crossing inside of the circle like this, just any kind of crossing, so like even up here, whatever it may be, if they're crossing, you have to always set it up that way. That this portion of the line times this portion of the line. Oh, you can't see because my hand. Sorry. And then this portion of the line equals this portion of the line times this portion of the line. So it was like L times A, or LA times AN equals KA times AM. Follow as your line goes. Okay, so I went 3x times 2x plus 2, right? Equals 15 times 8.
Would it matter like which line you started with?
No, it doesn't matter at all. Okay, but the lines have to be crossing, and you have to care about the line segments in that case. Okay, so then I would factor this. I would say two numbers that multiply to get negative 20, but add to get 1. Well, that's going to be positive 5 and negative 4. So I set them to 0 and I solve. So I get x equals negative 5. I get x equals positive 4. Which one do you think is the answer? It's what? Right. We're talking about measurements here. Okay, negative's not going to work. So if we're talking about line segment, it has to be a positive answer. So you would look at x equals 4. Okay. If you're not comfortable with the factoring, that's fine. I'm not saying you have to be. I'm going to zoom out just a little bit so we can see this. You're going to say 6x squared plus 6x minus 120. You graph it, and notice where it's hitting. It's hitting at our negative 5 and our positive 4. The negative one, yet again, you're throwing out because of negative measurements, so positive 4 would have been your answer. So anytime you're trying to find a solution, solve for x, you have the option of graphing. Okay, if you see that your solution is a giant solution, though, it's not like a normal 4 or something, then you may want to reconsider because it's going to be harder to find on your actual calculator. But that's up to you. I leave that up to preference. Okay, I'm going to talk about graphs really quick. of circle. This is the answer key instead of the actual paper I need, but whatever. That's fine. It doesn't matter. Standard form is this kind of format. X minus a number squared plus y minus a number squared equals some number. And what happens is it tells you the center and the radius. It's technically x minus h squared plus y minus k squared equals r squared, where hk is my center and r is my radius. Notice that h and k both switch signs, okay? I told you before, anytime it comes out of that parentheses, it's going to switch signs. So when I look at number 22 and I'm trying to find the center, which I know the answer is right there because I gave you the answer key, you're going to switch the signs. You pull out 4 and it becomes positive, and then the 2 becomes a -2. So my center was at 4, -2. My radius is whatever the square root of this is. So 9 becomes 3 in that case. Is there questions about that? You should be able to also go in reverse. You should be able to, I want to find a good example. You should be able to write the equation. Does anybody still need to see that? Okay, so if I was writing the equation, this is what I'm given. Oh, let's get away from those. Number 24, I'm told the center and the radius. I should be able to go x minus a -6 comes plus, then squared, plus y minus 1 squared equals whatever 7 squared is, which is 49. And that would be my standard form. So you should be able to write the equation as well as find the center and the radius. You should be able to go both ways. You should be able to draw the graph from it. Obviously, it's not going to have a constructor response, so it's not going to ask you to draw the actual graph. I'm not going to go over it for time's sake. If it gave it to you in a non-standard form, some of you this may make sense, some of you it may not, because we have different levels of students in here at the moment. You would have to complete the square. So you'd have to complete the square of x and y by making perfect square trinomials in 2 sections. If you want an example of that, I will give it to you, but I don't want to do it class-wide I don't want to cause confusion. I don't think they'll ask that, but if they do and you want to be prepared for it, if you just see me, I will be more than happy to work with you on that. It won't take but a minute. Okay, so that covers all circles that I can think of. I'm going to talk about sine, cosine, and tangent being our big ones that we really need to focus on. You should be able to solve for a degree or solve for a side. Either way. So I'm going to draw an example. First of all, remember sine equals opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Oh, I'm zoomed in, sorry. I probably should have wrote it this way. Now, there's a couple of sayings, whichever one you want to use to remember it, or just know it. I don't care which way you go. But if you know sine, cosine, and tangent, you should also know cosecant, because it's reversed, secant, and then cotangent. If you don't know those, commit them to memory. Okay, I remember by thinking of SOHCAHTOA. Sine, opposite hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. You could just remember OA. I think that's also how it's taught to me. And then if you're the one that wants to do the some old hippies caught another hippie dripping on acid, that's fine. I don't care. It's not my favorite, but you know, it's whatever. Makes you happy. Okay.
Hippie's definitely happy.
Do what?
The hippie's definitely happy if he's tripping on acid.
That's true. Or he's freaked out. You have options.
Yeah, only two.
I mean,
That,
it depends. Depends on what level he's at, I guess. I don't know. Never had experience.
ultimately.
So we're going to say we want to solve for x, and we know that this is 25, and we know that this is 34 degrees. You have to look at it and say, I need to figure out which one I can use, but I have to figure out what I have and what I need to know. Okay, so I know 34 degrees, I know 25, and I need x. Using 34 degrees, so this is the angle that we're using. What is x compared to 34? Opposite, adjacent, or hypotenuse? It's opposite. What is 25? Adjacent. And this would be hypotenuse, but we don't even need that one, so we're not really going to worry about it. Well, the only option I have that has opposite and adjacent is tangent. So I'm going to have to say tangent at 34 degrees equals opposite, which is x, over adjacent, which is 25. You cannot just pick willy-nilly which one you want just because you like sine better. You can't just pick it. You have to see which one you need. Okay. From there, you would just find tangent 34 multiplied by 25. And what should your calculator be in? What mode? Yeah, degree. Now, if instead of 34 degrees, I gave you the radians for it, make sure you're in radian mode. Degree mode will always have the degree on it. Radian mode will state it in some way. Okay, so we have 25 tangent of 34, and I don't think I checked my mode. See, I'm in radian, so practice what I preach. And you get 16.86 or 16.9 would be x. So you have a question about that? You may also go the opposite way. You may have to find the actual degree. So an example of that would be, this is 16, and we're going to say this is 39.3. And I want to find this degree. It's an O with a line through it. It's theta. It's theta. Don't know how you're seeing a 2 or an 8, but I'll go with it. Okay, so you're going to look at it and say, compared to my angle, what do I have? Because it matters where the angle is compared to what you're using. Because at this angle, this is adjacent. But if I was using this angle, it would be opposite. So you have to think about it for that specific angle. So we have adjacent and we have hypotenuse. What is that going to use? Cosine. So cosine of whatever degree, the degree always goes with the sine, cosine, or tangent, equals 16 over 39.3. Well, if I could write, that'd be great. Okay, we usually know that you have to always do the opposite operation to be able to get it loose. Well, cosine of theta is a unit, right? It's like cosine of theta. It's not just cosine times theta. So to undo cosine of theta, you have to do the inverse of cosine. That means on your calculator, still stay in degree mode because you need to find the degrees, you're going to hit second cosine, and it does that to the power negative 1. That is inverse. Then you type in 16 divided by 39.3, and you get about 66 degrees. And that's your answer. Is there questions about that? Okay, I don't think we need to go through them, but you can correct me if I'm wrong. Don't forget that you have like side, angle, side, congruence, and stuff like that. Remember, any of those work. The only thing, my trick is, it cannot spell a bad word either forward or backward. So if it says ASS, it's not a legitimate rule. If it says SSA, so backwards, it is not a legitimate rule. Okay. Any other combination of angles and sides works. So side, 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 angle, side, stuff like that works, but you cannot be able to spell, ass forwards or backwards. And I think you know the word and you've said it 1,000 times. So, anyways, okay. Does anybody need to go over anything else they can think of? Are we good with Pythagorean theorem? A squared plus b squared equals c squared. It is your friend. Don't forget it. Because I have to say it a billion trillion times in my life. Okay, go away so we can all have a weekend. Yes. Are you going to be here on the review day? Before the test? Okay, just show it to me then. If not, show it to me on test day.